Can gravity push things away?
The fake anti-gravity, created by quantum gravity. Gravity always pulls us in. An object released from your hand falls to the ground.
The moon remains in orbit around Earth. And Earth cannot escape the gravitational influence of the sun.
Gravity is one of the most familiar forces in the universe, yet it is also one of the hardest to overcome.
That is why humanity has long dreamed of anti-gravity, floating cities, spacecraft rising without fuel, and machines capable of reversing gravity at will. But a recent theoretical study asks a fascinating question. Even if gravity always attracts, could quantum mechanics make an object appear to move as though gravity had pushed it away?
The paper is titled
Repulsive Gravitational Force as a Witness of the Quantum Nature of Gravity. At first glance, the title sounds as if gravity itself might change from attraction to repulsion. It may even seem to suggest the first theoretical step toward anti-gravity technology. But let us clarify the conclusion from the beginning.
This paper does not propose an anti-gravity engine.
The sign of gravity does not actually reverse. No mass produces genuinely repulsive gravity. The apparent repulsion discussed in the paper is a conditional shift created through quantum superposition, interference, and a process known as post-selection. Even so, the study is important. That small apparent reversal may provide evidence that gravity is not merely a classical force, but something capable of participating in quantum superposition and interference. In this video, we will explore what this effective gravitational repulsion really means, whether it could ever lead to anti-gravity technology, how difficult such an experiment would be, and how it might be interpreted from the perspective of information gauge effective field theory, or IGEFT. Modern physics contains a strange imbalance. Electromagnetism has been quantized. Light carries energy and information in quantum units called photons. The strong and weak nuclear forces are also described using quantum field theory. Gravity, however, is different. In general relativity, gravity is not simply a force. Mass and energy curve spacetime, and objects move along paths determined by that curved geometry. General relativity successfully explains planetary motion, the bending of light, black holes, and gravitational waves with extraordinary accuracy. But it remains fundamentally a classical theory. Atoms and elementary particles, on the other hand, obey quantum mechanics. A quantum particle does not always occupy one definite location. It may exist in a superposition of several possible positions. Two particles may also share a single entangled quantum state, even when separated by a large distance. This raises a profound question. Suppose a massive object is placed in a superposition of two different locations. Would the gravitational field produced by that object also exist in a superposition? Or would gravity refuse to become quantum and produce only one classical averaged field? This is not merely a philosophical puzzle. If gravity can preserve or transmit quantum superposition, we would gain important evidence that gravity itself possesses quantum degrees of freedom. One well-known proposal for testing this idea places two small masses into spatial superpositions. Imagine that each mass exists simultaneously along a left path and a right path. The distance between the two masses then depends on the combination of paths they occupy. Because the distance changes, the gravitational interaction between them also changes slightly. After sufficient interaction time, these gravitational differences may generate quantum entanglement between the two masses. If gravity is the only interaction linking them and entanglement is observed, then gravity must be capable of carrying quantum information.
That is the basic logic. But such an experiment is extraordinarily difficult. Both masses must be placed into spatial superposition. Both must remain coherent and isolated from the environment for a sufficiently long time. Finally, an extremely small amount of entanglement must be measured. The new paper asks a more economical question. Could the quantum nature of gravity be detected by placing only one mass into a spatial superposition? The proposed experiment begins with a source mass. This mass is prepared in a superposition of two spatial paths, one on the left and one on the right. This does not mean that the mass is secretly located on only one side and that we simply do not know which one. Quantum mechanically, before measurement, both possibilities coexist and may interfere with each other. A much smaller probe mass is placed nearby. When the source mass follows the path closer to the probe experiences a slightly stronger gravitational attraction. When the source follows the more distant path, the probe experiences a slightly weaker attraction. The probe therefore receives two possible momentum kicks. In one branch, it is pulled somewhat more strongly toward the source. In the other branch, it is pulled somewhat less strongly. So far, nothing appears unusual. In both branches, gravity remains attractive. At no point does gravity push the probe away. But then, the two paths of the source mass are recombined. Among the possible final measurement outcomes, only one specially chosen result is selected. And something surprising may happen. When researchers examine only those selected events and calculate the probe's average momentum, the probe may appear to have moved away from the source. Gravity attracts the probe in every individual branch, yet the conditionally selected average can point in the opposite direction. How is that possible? In the classical world, alternative possibilities are usually combined as ordinary probabilities. If one force pulls strongly and another pulls weakly, we simply calculate a weighted average. But quantum possibilities do not combine merely as probabilities. Before a measurement is made, probability amplitudes are added. A probability amplitude has not only a magnitude, but also a phase. When two amplitudes meet, they may reinforce one another or cancel one another. Think of two water waves. When one crest meets another crest, they form a larger wave. But when a crest meets a trough, the two waves may cancel. Quantum interference works in a similar way. The momentum wave associated with the strongly attracted probe and the momentum wave associated with the weakly attracted probe overlap with a particular phase relationship. In some regions of momentum space, the two contributions cancel. In other regions, they reinforce one another. As a result, the center of the remaining distribution may shift beyond the range suggested by either branch individually. It is somewhat like two people both pointing to the right, yet when their shadows are superimposed in a special way, the resulting silhouette appears to point to the left. Neither person actually pointed left. The strange result is created by how the two possibilities were combined and by which final outcomes were selected. That is the effective repulsion discussed in the paper. And this distinction is essential. Gravity never becomes repulsive along any individual path. The law of gravity is not violated. Negative mass is not created. The force itself does not change direction. The apparent reverse motion arises from quantum interference and post-selection. In ThothSaem's interpretation, nature has not broken its law. Instead, it has revealed that what we call an average result can display a completely different face depending on how possibilities are combined and which events are selected. In the quantum world, reality is shaped not only by the possibilities that survive,
but also by the possibilities that cancel and disappear. The technique that can make this tiny effect visible is known as weak value amplification. The name may sound as though it refers to a weak effect, but it is actually a method for making an extremely small interaction appear much larger under carefully selected conditions. First, a quantum system is prepared in a chosen initial state. After the interaction, only a very particular final state is selected. When the initial and final states are almost mutually exclusive, successful events become extremely rare. But among those rare, successful events, the average shift of a measured quantity can become unusually large. The structure is somewhat similar to a lottery. The probability of winning is extremely small, but if we examine only the winning cases, the average reward looks extraordinarily large. However, weak value amplification does not strengthen gravity itself. It does not increase the total gravitational energy in the experiment. It does not cause every probe particle to move farther. Only the selected subset of events displays an amplified average shift. Amplification therefore comes at a price. The greater the amplification, the lower the probability of successful post-selection. To obtain sufficient statistics, the experiment may need to be repeated hundreds of thousands or even millions of times. Small asymmetries in the detector or tiny errors in the selection process could also create false signals that imitate the apparent repulsion. Weak value amplification is therefore not a magical magnifying glass. It is better understood as a highly selective filter that makes a faint signal more visible while discarding most of the experimental events. Could this phenomenon eventually become an anti-gravity technology? At present, the answer is clearly no. What we normally mean by anti-gravity technology is a device that produces a persistent force opposite to gravity. A spacecraft should rise against Earth's gravity. A heavy object should remain suspended without ordinary support. The effect should be repeatable, scalable, and independent of selecting only a rare subset of measurement outcomes. Most importantly, when the entire system is considered, there must be a genuine net force, momentum transfer, or lifting capability. The effect proposed in this paper does not meet these requirements. The apparent repulsion occurs only in a selected fraction of events. When the unsuccessful events, the source mass, the detector, and the entire experimental apparatus are included, total momentum remains conserved. The selected data may make the probe look as though it has been pushed away, but the apparatus as a whole does not acquire continuous propulsion in one direction. This effect cannot lift a spacecraft. It cannot suspend a macroscopic object. It cannot be used as a gravity shield. The gravitational field has not been removed or weakened. What changes is the interference between two quantum possibilities created by slightly different gravitational interactions. Still, that does not mean the effect has no technological value. It could contribute to quantum sensors capable of measuring extremely small forces, conditional signal amplification, precision interferometry, and null tests of new gravitational theories. It is not an anti-gravity engine. It is closer to a microscope designed to reveal the quantum character of gravity. Whenever humanity discovers a new phenomenon, we immediately imagine how it might be used. After discovering fire, we imagine engines. After discovering electrons, we imagine computers. But not every discovery becomes a machine immediately. Some discoveries first provide a new language for understanding nature before they become tools for controlling it. The apparent repulsion in this paper belongs more to that category. Can this experiment be performed with current technology? The proposal requires a small source mass, possibly a nanoparticle, to be placed in a spatial superposition. A smaller probe is positioned nearby. The system must then maintain a weak gravitational interaction for a fraction of a second or longer, depending on the detailed setup. Some of the required technologies have advanced significantly. Researchers can trap nanoparticles in vacuum. They can cool motion using lasers and electromagnetic fields. They can measure the momentum and position of atoms and microscopic objects with extraordinary precision. Scientists are also exploring ways to control the spin inside nanodiamonds and couple that spin to the motion of the particle. But the central bottleneck remains enormous. The challenge is not merely to move a nanoparticle between two locations. The particle must genuinely occupy a coherent superposition of two separated positions. That superposition must survive long enough for the tiny gravitational effect to accumulate. A single collision with a background gas molecule can leak information about which path the particle occupied. Thermal radiation emitted by the particle, mechanical vibrations, magnetic noise, and fluctuations in electric fields can all destroy the superposition. The more massive the object becomes, the more strongly it tends to interact with its environment. Distance creates another severe difficulty. Gravity is extremely weak, so the source and probe must be placed very close together. But at separations of hundreds of nanometers, electromagnetic and surface forces may become far stronger than gravity. A tiny residual electric charge can overwhelm the gravitational signal. Small variations in surface potential, magnetic impurities, and vacuum-induced forces can also imitate or obscure the effect. So, the greatest experimental problem is not simply detecting a tiny momentum shift. It is proving that the shift was genuinely caused by gravity. Researchers would need to show that the signal disappears when the source mass is no longer in a superposition. They would need to vary the relative phase between the two paths and verify that the signal changes in the predicted manner. They would also need to test how the effect scales with distance, interaction time, and mass. Current technology is approaching some of the individual ingredients, but it has not yet integrated them into a complete experiment capable of revealing this quantum gravitational signature. The proposal should therefore be viewed not as a device ready to be built immediately, but as an experimental direction that may become accessible as massive quantum superposition technology improves. Now let us consider the experiment from the perspective of information gauge effective field theory, or IGEFT. First, an important clarification is necessary. The following interpretation is not a conclusion of the original paper. It is a speculative theoretical extension inspired by the experiment. In the standard proposal, the source mass follows two quantum paths. Along each path, the probe receives a slightly different gravitational interaction. When these alternatives are recombined, their relative phases produce interference. Post-selection can then shift the average momentum of the probe in the apparently repulsive direction. From the viewpoint of IGEFT, we may ask whether an additional layer of structure could exist. The path followed by a quantum system may represent more than a difference in spatial position. Along each path, the quantum state may acquire a different informational history, different correlations with the environment, different patterns of entanglement, different coherent structures, and different records of state preparation. IGEFT explores the possibility that these informational histories may couple to an additional gauge-like connection. In simpler language, two paths may begin and end at the same physical points, yet accumulate different informational traces along the way. Ordinary gravity responds to mass, separation, and duration. IGEFT asks whether nature may also respond, however weakly, to the way quantum information is arranged and transported along those paths.
If so, the two gravitational branches could accumulate not only ordinary gravitational phase differences, but also a small information gauge phase. That extra phase might slightly shift the interference pattern or modify the momentum amplification produced by post-selection. Even if the mass and spatial geometry remained unchanged, changing the internal quantum state or the degree of entanglement might then alter the final momentum distribution. One could also search for a holonomy-like residual, a signal that changes sign when the order or orientation of the information path is reversed. Let us take one more step in the ThothSaem interpretation. We usually understand nature through the motion of objects in space. We ask where an object was, how fast it moved, and what forces acted on it. But in the quantum world, position alone is not enough to describe a physical state. We must also ask what the system was entangled with, which possibilities were able to interfere, and what information leaked into the environment. Perhaps at the deepest level of nature, spatial geometry and informational relationships are not completely separate. If gravity reads the geometry of space, then IGEFT asks whether nature also reads the informational history of quantum states moving through that space. However, this interpretation faces a major scientific challenge. It is not enough to say that an information gauge phase might exist. The theory must calculate how large the effect should be, under which conditions it appears, under which conditions it vanishes, and how it scales with distance, time, coherence, and entanglement. Experiments require numbers. They require predicted signs, magnitudes, scaling laws, and null conditions. Without these, the IGEFT interpretation remains a conceptual possibility rather than a testable physical theory. An even greater problem is that any IGEFT signature would probably be smaller than the basic quantum gravity signal itself. This experiment contains several nested layers. The largest layer consists of background forces, electrostatic effects, magnetic interactions, surface forces, thermal fluctuations, and mechanical vibration. Hidden beneath those backgrounds is the much smaller quantum gravitational interference signal predicted by the paper. If an IGEFT contribution exists, it would likely appear as an even smaller residual on top of that already tiny quantum gravity effect. The first task would therefore be to detect and characterize the standard effect with high precision. Only then could researchers search for a small difference between the measured data and the standard prediction. But even if such a difference were found, it could not immediately be called evidence for IGEFT. It might come from an error in distance calibration, residual electric charge, detector bias, imperfect post-selection, or unmodeled decoherence. That is why the best IGEFT signature would not be a simple additional force. It would need a distinctive pattern that ordinary systematic errors find difficult to imitate. For example, the physical masses and spatial paths could be kept fixed while only the quantum information preparation is changed. If the residual depends systematically on the information state, that would be more meaningful. The direction of the path could be reversed. The standard gravitational contribution might remain unchanged, while a holonomy-like IG term changes sign. Researchers could also vary the post-selection condition continuously and test whether the measured curve departs from the standard weak value prediction in a specific pre-calculated form. The important question is not merely whether the signal becomes slightly larger or smaller. The strongest evidence would be information state dependence, orientation reversal, a closed-loop residual phase, or a precisely predicted null condition that cannot easily be reproduced by conventional forces or detector imperfections. This paper does not announce the birth of an anti-gravity machine. It does not describe a way to block gravity, reverse gravitational attraction, or suspend objects in the air.
Along every individual branch, gravity remains attractive. Yet when two quantum alternatives interfere and a particular outcome is post-selected, the average momentum of the probe can shift in the direction opposite to gravitational attraction. This small paradox leads us to a profound question. Is physical reality merely an average of events that occurred along separate paths? Or is the final outcome created by the entire network of quantum relationships, including possibilities that were never individually realized and amplitudes that canceled one another? In the classical world, causes appear to precede effects in a straightforward way. Push a ball, and it moves. Pull an object, and it approaches. But in quantum mechanics, the meaning of an intermediate interaction may depend on how the complete experiment is prepared, recombined, and measured. This does not mean that the future rewrites the past. It means that the physical meaning of one part of an experiment is defined within the relational structure of the entire process. ThothSaem views nature as a vast sentence written in information. A single word does not possess its full meaning when isolated from the sentence. It acquires meaning through its relationship with the words before and after it. A quantum path may be similar. Each branch, considered alone, produces only attraction. But when it interferes with another branch and becomes connected to a final measurement, the combined result can appear repulsive. Nature may not be merely a collection of isolated events. It may be a structure of relationships. And gravity, at its deepest level, may transmit not only the influence of matter and geometry, but also the organization of quantum information. What this paper offers is not a blueprint for an anti-gravity engine. It offers a new way to ask whether gravity can transmit quantum possibilities, whether those possibilities can interfere, and how that interference becomes an observable result. The experiment remains extraordinarily difficult. Even the basic quantum gravity signature has not yet been observed, and any additional IGEFT effect would likely be hidden at an even smaller scale. But the history of science has not advanced only through dramatic, easily visible phenomena. A tiny bending of starlight helped confirm the curvature of space-time. A minute shift in an atomic energy level revealed new quantum effects. Perhaps one day, an almost invisible reversal in the momentum of a microscopic probe will reveal the quantum nature of gravity. And if that reversal contains a reproducible trace that depends on informational state rather than mass and geometry alone, we may encounter a deeper grammar of nature, one in which space and information are not entirely independent. Is gravity merely the attraction between masses? Or is it a deeper field that records and transmits relationships between space-time and quantum information? This study does not yet provide the final answer. But good science does not always begin with a completed answer. Sometimes it begins by making a new question possible. From within the familiar fact that gravity pulls everything inward, the quantum world may be whispering something unexpected. Not every motion away is evidence of a repulsive force. And not every attraction must appear as an approach. Reality is shaped not only by the direction of forces, but by how possibilities are connected, allowed to interfere, and finally selected. Thank you for watching. From ThothSaem's Science Catch.